Hello everyone, welcome back to another video. On today's problem we are going to be looking at a situation where we're going to have a wind or a fluid flowing through a turbine, and that turbine is going to be spinning in order to generate power, and we are going to be taking a look at what the ratio of the inlet velocity and the outlet velocity is going to be in order to generate the highest possible amount of power, alright? And we know that that is already going to be 1/3, all right? So the outlet velocity is going to be 1/3 of the inlet velocity, and that is when we are going to have maximum power generation, all right? And now we are going to be using some derivations in order to show why that is the case, all right? So in this situation, we are going to have a certain density of air. The density of the air or fluid is going to be remaining constant throughout this problem, and it is going to be coming in at an area A1, and then it is going to move through this turbine where it's going to be getting all rolled around and messed up and everything, and then it's going to come out on the other side at this larger area A2, and it's going to come out in this larger area A2 because the velocity is going to become lower as some of that kinetic energy gets used up by the turbine in order to generate the power, right? So we know that the density is going to be remaining constant, and the only real variables we are going to have in this problem is the area which it is entering and exiting over here, and also the velocity. It is going to be slowing down as it comes out of the blade, all right? So we have three areas that we're going to be using to solve this problem. We have our A1 right here, which is sort of the inlet path right here. And then we have the exit path right here, A2. And then we also have this area right here, which is actually the area surrounding the blade, where it is going to be coming in contact with the blade, all right? So the first step in order to figure out what the ratio of the outlet velocity and the inlet velocity is going to be to do a momentum conservation equation, all right? We know that momentum is going to be getting conserved when power generation is at its most efficient point, its max point, because no energy is going to be getting lost to the system, right? So we're not going to have we're not losing any air through this system. All of the air is going to be retained throughout this system, right? It's not going to be spreading and going out. It's going to be staying in this conserved system, all right? And we know that momentum is going to be conserved because that is when we are going to have our most efficient energy production, all right? And our momentum equation is, again, mass times velocity. So when momentum is going to be conserved, that means that the change in momentum over the change in time is going to be equal to 0. All right, so we'll go ahead and write that out. So the derivative of the mass of the system multiplied by the velocity of the system over dt, this is going to be equal to 0 because momentum is going to be getting conserved throughout this process, all right? And another way to express that is that the V in multiplied by the V out subtracted, or excuse me, the velocity in multiplied by the area going in, or the mass going in, excuse me, subtracted from the velocity going out multiplied by the mass going out, and then that is also going to be added to the force, all right? So that is another way we can express this. So we can go ahead and write that out. Go ahead and put the 0 over here to get some room. All right, and then this is all going to be added by the force that is being put on the system. All right. All right, so this mass flow rate, this is just going to be the rate that mass is entering the system and mass is exiting the system. This is going to be a rate, and it is going to be the exact same starting and entering. So we can go ahead and factor this out, right? And then since we know that this is going to be equal to 0, we can go ahead and subtract f from both sides to get f on its own. So this is going to become negative F, and then we are going to factor out this mass flow rate out, and then we will be left with the velocity going in minus the velocity going out. Alright, so for this mass flow rate, we are not going to be given that, but we can go ahead and figure it out from other terms which we are going to know. We know that this mass flow rate is going to be equal to the density, this density over here, and then that is going to be multiplied by the actual flow rate Q, and that is going to be the same as this mass flow rate, so we'll go ahead and write that out. Then this is multiplied by the actual flow rate. And again, we're not going to be giving this flow rate, but once again, we are going to have terms that we can substitute in for this, which is simply going to be the velocity of the fluid or air, and then that is going to be multiplied by the area where that velocity is being taken, and that will give you the flow rate. So we'll substitute that in as well. So Q will become VA. So the mass flow rate will be equal to the density multiplied by the velocity multiplied by the area right there. And this can be taken at any area, whether it's A1, AB, or A2, right? Alright, so now we're going to later go ahead and substitute that in for our mass flow rate. And the next thing we're going to want to do is we're going to want to take a look at what power actually is. So in order to know when the power production is going to be most efficient, we'll go ahead and break down what exactly power is. And power is actually the rate of energy over time. All right, so we'll go ahead and write that out. So power equals energy over time. Okay. And another way to express this is just the kinetic energy, the change in kinetic energy over the mass multiplied by the mass flow rate. So that is another way to express this. Change in kinetic energy over mass multiplied by the mass flow rate. And then when you think about power in terms of force and velocity, this is going to be equal to negative force times velocity. All right, so now that we have our expression for the power, we can go ahead and erase this over here. All right, and next thing we're going to want to do is we're just going to substitute in over here. Our PVA is going to be going in down here for our mass flow rate, and then we will use our equation up here for our negative F. This works out nicely for us because we have a negative F down here and a negative F down there. So that's already going to be accounted for. This is going to become positive. All right. And then for our change in kinetic energy over mass, we do have an equation that we can substitute in for this. The change in kinetic energy over mass is going to be equal to V1 squared minus V2 squared over 2. So we can go ahead and write that out. So this is going to be getting substituted in over here for change in kinetic energy over mass. All right, and we'll go ahead and start substituting some things in. We'll go ahead and start on a new line. All right, and then we substitute in our density, velocity, area for the mass flow rate. All right, so this right here, this is going to be taken at the velocity and area of the blade. So this is going to be VBAB. All right, and then over here for our negative F, we'll go ahead and substitute in our expression for the mass flow rate and for that equation as well. And then this is also going to be at the area of the blade and the velocity at the blade. And then this is going to be the velocity of the blade too. So this is going to become VB squared right here. So this will be rho VB squared AB. This is going to work out nicely. We're going to have lots of things canceling out for us. This is all going to cancel. Squared's going to cancel. And we're just going to be left with a VB over here. So this is going to become VB equals V1 squared minus V2 squared over 2. Oh yeah, it looks like we did forget our V in minus V out over here. So that should be right here getting multiplied on the right side. So that means that would stay over. And then that would end up getting divided over in order to get VB by itself. So VB is actually going to be 1/2 V1 squared minus V2 squared all over V1 minus V2. Alright, and if we look at V1 squared minus V2 squared, that's going to be a difference of squared. So this is actually going to be able to factor out into V1 plus V2, and then V1 minus V2. Alright, and then that would again all be over V1 minus V2. So those are going to cancel out right there, and we're just going to be left with V1 plus V2 at the top, and then that is all going to be over 2. So we'll go ahead and write that out. Alright, and there you have it. This is going to be our expression that gives you velocity of the blade in relation to the velocity at the area 1 and the velocity at area 2. This is really just an average right here. If you look at it, you're adding the velocity here and the velocity here and dividing by 2. This is the average velocity between the two velocities right here, alright? Alright, so our next step is going to be plugging in this expression for VB back into our power equation, which was this left side right here. We'll go ahead and erase all of this out over here, clear up some room for ourselves. Alright, so this was power right here. We'll just go ahead and write it out fresh up here. So power equals 1/2 V1 squared minus V2 squared, and then multiplied by our mass flow rate. Density times VB AB. Alright, and then what we are going to do is we are going to substitute in this expression right here, VB, and over here. So this is going to be coming in right there. We'll go ahead and write that out now. So we are going to have this 1/2 that's going to be coming in, and we can go ahead and multiply that by this 1/4 over here. So power is going to be equal to 1/4. And then we will go ahead and bring in our density and area to the front. So density, area, and then we had V1 squared minus V2 squared. And finally, at the end over here, we're going to have V1 plus V2. Alright. So, our next step is going to be to multiply out these velocity groups over here in order to create one big polynomial expression. So we'll go ahead and do that now. Alright, so this is going to become V1 cubed. Then this will become plus V1 squared V2, and then minus V1 V2 squared, and then minus V2 cubed. Alright? And what we can do now is we can go ahead and take out a common denominator over here, this V1 cubed, and we'll see what that leaves us with. So we'll pull a v1 cubed out of all of these terms and pull it out front. Alright, so obviously you take a v1 cubed out of v1 cubed, you're just going to be left with 1. And then right here, this is going to become a v2 over v1. Over here, this will become negative v2 squared over v1 squared. And right here, this will become negative v2 cubed over v1 cubed. All right? So if you think of these v2 over v1s as just a constant expression of the ratio of the outlet velocity and the inlet velocity and give it a variable like r to represent v2 over v1, you can see that these are really all just the same term except increasing in exponent as you move along, all right? So what we can do is we can assign a variable to equal v2 minus v1. In this case, it will be r. So we will say r is equal to v2 over v1, all right? And when we do that, we can just see that this is going to be r to the 0, r to the 1, r squared, and r cubed. So we can go ahead and write those out. Okay, so our next step is actually going to be to take the derivative of the power with respect to time, all right? Because we know that when power is at its highest efficiency is when that power isn't going to be changing with time. So we're going to take this derivative with respect to time and then set that equal to 0. And then whatever value we get for this r is going to tell us the ratio of the outlet velocity to the inlet velocity at which we get no change in power over time, which is going to mean that the power is being maximized and at its most efficient value, all right? So we can go ahead and do that now. We'll go ahead and erase all of this up here. All right, so we are going to be taking the derivative of power with respect to time, and that is going to be equal to the derivative with respect to time of this term right here, and this the density is going to be constant as well as the area at the blade, and the velocity going in is also going to be constant. So this term right here is pretty much going to be one big constant that we are not going to have to worry about when we express this derivative. So we can go ahead and pull that out front. All right, and then we will get dt of 1 plus r minus r squared minus r cubed. All right, and then when we do this, this derivative is going to become, this is going to become 0, 1 will go away, the r will become 1, this r squared will become negative 2r, and then this will become negative 3r squared. So we'll go ahead and write that out. And again, this is going to be equal to 0. So 0 is going to be equal to 1 minus 2r minus 3r squared. All right, and then from here, we can figure out what the values for r are going to be that get this to equal 0. So we can just do some simple factoring, and when we do that, we will get negative 3r, and then an r, and then these will both be plus 1, plus 1. And that is all going to be equal to 0. So when the power is as most efficient is going to be when R is equal to 1/3 and R is equal to -1. But when we look at -1 here, that means that the speed at the inlet area is going to be equal to the velocity going outwards, but in the opposite direction, which doesn't really make sense, right? That means that you're going to have equal velocities going in on each side, which means the turbine isn't going to spin at all and no power is going to be generated. So -1 isn't the correct answer here that we're looking for. The correct answer here is 1/3. Which again, when we look at what R actually is, it is the ratio of the outlet velocity to the inlet velocity. So this means that power is at its most efficient value when the inlet velocity is 3 times the value of the outlet velocity, all right? So that is how you mathematically explain why that is the case. And if you guys have any questions, make sure to leave them in the comments. If you enjoyed the video, leave a like on the video. Subscribe to the channel if you guys want to see more content, and make sure to have a good day.